Good evening, ladies and gentlemen. Welcome to the distinguished lecture of Artificial Intelligence for Massive Internet of Things, organized by IEEE Sri Lanka section. This is organized as a part of an annual activity of IEEE Sri Lanka section, where we try to bring distinguished lecturers, prominent lecturers from all over the world, and create a platform to share their knowledge, skills among our Sri Lankan community. So to introduce today's distinguished lecturer, I would like to introduce our IEEE Sri Lanka section chair, Dr. Maheshi Disanayaka. Dr. Maheshi Disanayaka received her BSc in Engineering degree in Electrical and Electronic Engineering from University of Peradeniya, Sri Lanka. And she completed her PhD at University of Surrey in 2010. And currently she is working with the Department of Electrical and Electronic Faculty of Engineering, University of Peradeniya, Sri Lanka. She is the founding chair of IEEE Women in Engineering Sri Lanka section and currently the chair of IEEE Sri Lanka section. Over to you, Dr. Maheshi.
Thank you, Vindhya. Good evening, everyone. So first of all, as the chairperson of Sri Lanka section, let me begin by welcoming all of you for today's distinguished lecture program hosted by the Sri Lanka section. I'm so pleased to be with you this evening and especially to host and have the chance to introduce our guest speaker, Professor Arumugam Nalanathan. Professor Arumugam Nalanathan, who is an IEEE fellow, is Professor of Wireless Communications and Head of the Communication Systems Research Group in the School of Electronic Engineering and Computer Science at Queen Mary University of London since 2017. He was with the Department of Informatics at King's College from 2007 to 2017, where he was a Professor of Wireless Communication from April 2017 till he joined the Queen Mary. He was an assistant professor in the Department of Electrical and Computer Engineering, National University of Singapore from August 2000 to December 2007. His research interests include artificial intelligence for wireless communication, 5G and beyond wireless networks, Internet of Things, and molecular communication. He has published more than 500 technical papers and is a co-recipient of the Best Paper Award presented at IEEE International Conference on Communication, ICC 2016, IEEE Global Communication Conference, GlobeCom 2017, and IEEE Vehicular Technology Conference 2018. Further, he is extending his service to the IEEE as an editor for IEEE Transaction on Communications and a senior editor for IEEE Wireless Communications Letters. In the past, he was an editor for IEEE Transaction on Wireless Communication, IEEE Transaction on Vehicular Technology, as well as IEEE Signal Processing Letters. He served as chair for the Signal Processing and Communication Electronics Technical Committee of IEEE Communications Society and the technical program chair and the member of the technical program committees in numerous IEEE conferences. He received the IEEE Communication Society's SPCE Outstanding Service Award in 2012 and IEEE Communication Society RCC Outstanding Service Award in 2014. He has been selected as the Web of Science highly cited researcher in 2016. Besides all these, he is a great mentor, a supervisor, and a research collaborator. I can vouch for him since I have the luxury of working with him back in 2015, and I'm so sure his students will say the same. So finally, he is also just a fascinating person, and we're all in for a great session today. So without further ado, please join me in welcoming Professor Nalanathan. Over to you, sir.
Okay, thanks Mahesh for the introduction. So I can share the screen. Okay, good evening everyone. So in this talk, so why do we need artificial intelligence for massive Internet of Things? So because artificial intelligence in many areas now, so why do we need artificial intelligence here in IoT? So most of you are familiar with the 5G and beyond 5G use cases, not like 3G, 4G. In 3G, 4G, the main concern only to increase the capacity. But in 5G and beyond 5G use cases, in addition to capacity enhancement, we have two more use cases. One is massive connectivity, other one is the critical IoT or ultra reliable low latency communications. If you take the enhanced mobile broadband to increase the data rate, there are numerous technologies. So massive MIMO, millimeter wave, numerous technologies available. So now in terms of massive IoT and critical IoT, numerous challenges have not been resolved yet. So that means even though 5G standard came, there are many unresolved challenges in massive IoT and critical IoT. So this talk is on massive IoT, one of the three pillars of 5G and beyond 5G cases. So that is on the bottom left corner pillar. So that is the massive IoT. So you may ask, so what is the difference between massive IoT and critical IoT? So the bottom two corners, so the requirements are completely different. If you take the massive IoT, so here we are going to have millions of devices or billions of devices are going to be connected to the internet. If you take critical IoT, here the applications are totally different. So here we have remote surgery, remote manufacturing, so autonomous vehicle. So here the requirements are reliability as well as latency, very low latency. But if you take the massive IoT, the requirements are totally different. So here latency is not an issue. Here the volume of data is going to be few bytes. So if you take electricity meter or gas meter, so the volume of data is going to be very small. But here we are going to have the devices, the huge number, say millions of devices are going to be connected. So if you take a particular household, you are going to have electricity meter, gas meter, so then the water meter, so then you may have CCTV camera. So in future that you may control your fridge or washing machine remotely, you can control. So there are numerous devices in every household are going to be connected to the internet. So if you see the growth from the Ericsson mobility report, you can see the massive IoT connections exponentially increases. So if you take by 2025, so in another 5 years, we are going to have 4-5 billion devices are going to be connected to the internet. Now the problem is how we are going to connect these devices to the internet. So we need wireless technology to connect these devices to the internet. So when you take the connectivity, so here the requirements are completely different from the human to human communication. If you take human to human communication, so mobile phone, every day we charge. But here the sensors, the lifetime of the battery should be at least 10 years. So the sensors, say if you take smart car parking, smart city applications, the sensor lifetime of the sensor battery should be at least 10 years. You cannot change the battery every year, 10 years. So if you take your handphone, you charge every day. So at the same time, here the network should support huge number of devices. At the same time, coverage should be around 15 kilometer range. Since we are going to have millions of devices. So here the development and implementation cost should be very low. So there are numerous technologies available for connectivity. So all these technologies are low power wide area network, not like human to human communication, not the cellular network, normal human to human cellular network. Here the network is low power because the lifetime of the battery should be 10 years. So the power should be very low power. So wide area network. So if you take many technologies available, LoRa, Sigfox, narrowband IoT, eMTC, so Bluetooth, Zigbee, numerous technologies. All these technologies we can put into two groups. One is the licensed band, other one is unlicensed band. For example, if you take Sigfox, LoRa, they are unlicensed band. So anyone can buy and anyone can install. You don't need to get the approval from the telecom regulation authority. You don't need. So anyone can buy LoRa for a few $1,000s. They can install a network with 100 sensors for a smart agriculture or wherever you can use it. But license based, if you take the 3GPP LTE based narrowband IoT eMTC standard, they are cellular based. So now the question is, say whether cellular based or whether licensed or unlicensed, the requirements are same. So that means if you see compared to human communication, so here the bandwidth is very small. So because few bytes of data, the range should be higher than the human to human communication. Here latency is not an issue. So here cost should be very low. So the requirements are completely different from human to human communication for massive IoT. Say now you can see the standard. If you see the standard licensed and unlicensed, first two columns, Sigfox and LoRa, they are unlicensed low power wide area network. So Sigfox, LoRa, anyone can buy. So the requirements in terms of data rate, lifetime of the battery, module cost, you can find all the details here in the standard. So if you take the third column and fourth column, they are LTE based. So if you take the third column and fourth column LTE based, for low data rate, we have narrowband IoT. For high data rate, we have eMTC. If you take low data rate, one resource block, 180 kilohertz. If you take eMTC for high data rate, we have 6 resource block, 1080 kilohertz. So whether you take first two column or third column and fourth column, you can see the lifetime of the battery is more than 10 years. So that's what here the network is low power network. Say if you can see the coverage, you can see 15 kilometer, 10 kilometer. So roughly 10 to 15 kilometer coverage. So now if you see the cellular based license and ISM band unlicensed. So if you take unlicensed band, you can see 1 and 2, the black boxes. You can see unlicensed spectrum. If you take Wi-Fi, Bluetooth, Zigbee, they are in box number 1. If you take the box number 1, so coverage, Wi-Fi, Bluetooth coverage is low. So we need 15 kilometer coverage. Here using Bluetooth, Wi-Fi, we cannot have 15 kilometer coverage. Coverage is low. So performance wise, okay. But if you take the unlicensed Sigfox LoRa, box number 2, if you use the Sigfox LoRa, so we have wide area network, coverage is good, but the performance is low. So, but if you take the cellular based one, if you take cellular based narrowband IoT, if you take it, the green box, so the coverage is much higher. So the performance much better than LoRa and Sigfox low power wide area network. So from this diagram, we can say that so cellular based narrowband IoT and eMTC are highly preferred in the urban areas. So say for example, if you take rural areas, agriculture, so you don't have the cellular infrastructure, you can use it Sigfox and LoRa. But mostly in urban areas, we have the well-developed cellular structure. So the cellular-based narrowband IoT and eMTC have much higher advantage compared to the unlicensed band. So because of that, So this talk, I am going to concentrate on the cellular-based for low data rate narrowband IoT, high data rate EMTC, the difference for low data rate and high data rate. So if you take the standard 3GPP standard from release 13, so in release 13, the narrowband IoT EMTC standard both were introduced. Then release 14, 15, 16, now 5G. So we have improved version of this narrowband IoT and EMTC. So now if you take this cellular-based standard, so already we have the cellular infrastructure. So we don't need new infrastructure. So the service cost is low, then scalability of the radio access network. So since we have many advantages here and here, so cellular-based IoT is preferred for massive Internet of Things. So now, so this is the introduction of cellular-based IoT, so for massive connectivity. Now the question is, so 3GPP developed the standard, so LTE-based standard. So then why do we need artificial intelligence? So I am going to show that the two motivations why we need artificial intelligence. First motivation. So now the problem is, the main problem is the two types of outage we are going to have. Because this is low power wide area network, since the power is low, unlike human to human communications, here the power is very, very low. So since the power is very, very low, from the sensor to base station, the received signal to interference noise ratio is going to be very low. Because of the path loss and fading, we are going to have SINR outage. Another one is collision outage, because to establish the connection with the base stations, the sensors, they are going to have preambles. So that means 54 preambles are available. So the devices are going to select the preamble and is going to send to the base station to establish the connection through the physical random access channel. So here we have these two outages. So if you see the electricity meter, water meter, vending machine, and the distance 500 meter, 1000 meter. So you can see the green blocks. So that means most of the resources are utilized to establish the connections from the sensor to the base station. E node B is the base station, IoT device to establish the connection. Now, if we take the traffic scenario, we are going to have different types of traffic scenario. So say if you take water meter, electricity meter, gas meter, they are fine. They are general traffic, no problem at all. So we don't need artificial intelligence for general traffic, because if you take electricity meter from your home, if the network is unable to send the meter reading now, it is not urgent. It can send it tonight. It can send it tomorrow. So for general traffic, this 3GPP based low power wide area network is fine. We don't need artificial intelligence. So where do we need artificial intelligence? For bursty traffic. So what is bursty traffic? For example, here the last one, pay as you drive. So pay as you drive. So for example, so if you take the car insurance, we now pay the fixed insurance every month. So some countries introduce pay as you drive, means so only when you drive the car only you have to pay the insurance. So that means when you take your car from your garage to the road, so the sensor in your car will try to establish the connection with the insurance service provider such that you can drive, you are allowed to drive on the road. So for example, if you take a big football match, 10,000 people, 10,000 cars leave from the stadium. All these 10,000 devices, the cars will, sensors in the cars will try to establish the connection with the base station. So here we have the preamble only 54. So these 10,000 devices will select one of these 54 preamble. So we are going to have collision outage. So how we can solve it? So if you take for the bursty traffic, if you take the standard 3GPP report, So the recommended model for this bursty traffic is time limited beta distribution. You can see during certain time slots. So time slots are going to be few hundred milliseconds. So within one time slot, few hundred milliseconds. So during certain time slots, so within 1 second, we are going to have numerous huge number of time slots. During that, we are going to have very huge number of packet arrival rate. So during those particular time slots within few seconds, so then what will happen? All these devices will select the preamble from the pool of 54 and they will try to send, then collision will occur. So they most of the devices, most of the sensors will not be able to succeed to establish the connection. So now, so whenever we want to implement something, or when before we deploy something, we have to do some mathematical modeling or mathematical analysis and to see how it works. So I'm not going to put any mathematical derivation or anything, just 2 slides. So we can model it, the scenario, using the spatial distribution of the system. We can model it. So if you see, the black dots are going to be the base stations. Blue dots are going to be the IoT devices. So mathematically, we can model it using the 2 homogeneous Poisson point process. If you mathematically model using the homogeneous Poisson point process, so the packets are going to arrive from the sensors. So say from the sensors, the packets are going to arrive. So when the packet arrive, so the sensor will try to establish the connection with the base station using random access protocol. So now the packet arrival, so in the time, so in the temporal model, we can model it as a independent Poisson arrival process. So if we model it the spatial distribution and temporal model, so we can see how the massive IoT network work under a bursty traffic scenario. So now, after mathematical modeling and mathematical derivation, if we get how, if you see a clear picture how this IoT network will perform under bursty traffic scenario. We consider a cellular network. So the density of the base station, within 1 square kilometer, we have 1 base station, for example. Number of preamble 54. So IoT devices, so randomly distributed, 15,000 IoT devices, 20,000 IoT devices. So they are going to establish the connection with the base station using well-known random access scheme. So if you take the cellular standard or Wi-Fi standard, so we have the general random access scheme, for example, back-off scheme, or power ramping scheme, or hybrid scheme. So that means if it fails, back off and increase the power. So this conventional random access scheme, so we select this conventional random access scheme under this scenario of 1 base station per kilometer squared, available preamble is 54, number of devices or sensors 15,000 or 20,000. So here, so we allow only 10 attempts. So 1 device will try to establish the connect, try 10 times. Beyond that, we can assume that packet drop, failure. So what we found is, so when we have 15,000 IoT devices, the success probability is going to be roughly 50%. So during that interval, bursty traffic interval, during that particular time interval, the bursty traffic comes. So success rate only 50%. So that means out of 15,000 devices, only 7,000, 8,000 devices will be able to establish the connection with the base station successfully. If you take the scenario of 20,000, 5,000 more, the situation is much worse. If you see 20,000, we are going to have random access success probability only 20%. So 15,000 to 20,000, so 20,000 only 4,000 devices will be able to establish the connection with the base station. So remaining 16,000 will not be able to establish the connection. For example, if you take a scenario of 20,000 cars leave, so 16,000 cars, they cannot drive immediately. So under this scenario, so how we can solve the problem? So this is one of the motivation. We need dynamic change of parameters. We have to change it dynamically. So this is one of the motivation for the usage of artificial intelligence in massive IoT connectivity under bursty traffic scenario. So the mathematical derivations I haven't included because that is, so here most of the audience from undergraduate students or from maybe with non-technical background. So that's what I haven't included. But if you are interested, you can learn the references. Now we are going to see the motivation 2. So one motivation I have shown. So under bursty traffic scenario, connectivity fail. Now we are going to see the second motivation. I take the standard. So we take the 3GPP based LTE based standard, narrowband IoT standard. So this is a low power wide area network, cellular based. So the optimized from LTE features. So optimized, so lifetime 10 years. So easy to implement, deep penetration, reliability. So huge number of devices can be connected. So this is the 3GPP narrowband IoT standard. If you take the IoT standard, so here, so in this IoT standard, the device, the sensor, will take a preamble and send to the base station to establish the connection. So once established the connection, only data can be transferred. So when you take the preamble, transmission time interval few hundred milliseconds. So here we consider 640 milliseconds, not second, millisecond. So in 640 milliseconds, so first certain time allocated for random access to establish a connection. So here narrowband IoT one resource block 180 kilohertz. 180 kilohertz is divided into 48 subcarriers. So each one is spacing is going to be 180 divided by 48. It is going to be 3.75 kilohertz. So here in the standard, preambles are transmitted to the base station as a group of symbols. So using frequency hopping such that we can have the frequency diversity. So here you can see 4 symbol group. They use the frequency hopping within this subcarriers. So now here the preambles in the standard, the preambles are repeated. So the repetition factor of the preamble can be 2 or 4 or 8 or 16 or up to 128 power of 2. Now the problem is if you increase the preamble repetition factor the high value, definitely we can establish the connection. But the problem is, for example, if we have the maximum repetition factor of 128, so in the allocated transmission time interval of say for example 640 milliseconds, so we are going to use several hundred milliseconds for random access. So we don't have the time to transfer the data. So therefore, so we cannot have the high value of the repetition factor. So if you take the narrowband IoT standard, there are 3 coverage extension group. So from the base station, the devices within the region of red, then next region green, the blue. So devices, all the IoT devices, so are going to be distributed within these 3 coverage extension group. So here for every coverage extension group, we are going to have 3 parameters. Say for red 3, green 3, blue 3 parameters. Those 3 parameters are going to be how many preambles are going to be in red, how many preambles are going to be in green and blue. Then what is going to be the repetition factor in green, red. So how many times we can allow the device to try again and again. So that is the random access opportunity. So if you see here, so 3 parameters, total 9 parameters. So these 9 parameters, if we have static, so then we won't be able to solve the problem. So because the traffic is going to be time varying traffic, because so few hundred sensors now active. Next second, those are inactive. So then the following second, there will be more 1,000 devices will be active. So this is every second time varying characteristic. So therefore, so at the beginning of every transmission time interval, so that is the packet time at the beginning, so these 9 parameters should be changed. So that means this resource configuration will be changed by the base station and broadcasted to each group. So red group, the resource configuration, the base station will inform to the red group. So these are the 3 parameters during this transmission time interval frame. So next one, it will be different. So the 9 parameters should be changed dynamically. So this is the communication procedure in narrowband IoT. So in a packet arrive in a sensor. So next one, so based on the received signal strength, so the base station knows that, okay, this device is red or green or blue based on the signal power transmitted from the device. Then it identifies the group. Then random access procedure. So there are limits. So here we are going to have the counters. So once the random access succeeded, only the last part, data transfer scheduling. So here, when we have these 4 procedures, each and every sensor, once the data packet arrives, each and every sensor follow these 4 procedures. So that means they are going to consume energy. So that means we know that, so the lifetime of the battery should be 10 years. So we cannot allow the sensor try again and again and again. So we have to limit it. So that means here we have energy constraint. So device should succeed to establish a connection while maintaining low energy consumption. Then delay also some, so we cannot have delay again for infinite delay we cannot have. So we have to limit, reduce the delay also. So here, so what we did, okay, earlier we haven't considered any standard in our motivation 1. So here in the motivation 2, so we considered the IoT standard, narrowband IoT standard, but we considered only 1 coverage region. So we haven't considered 3. If we consider 1 coverage region, so number of preambles like earlier 54, base station density, and E0B is the base station IoT. They are in the 100 by 100 kilometer area. So 10 to the power 4 kilometers square, the circle area. So the packet arrival, so we can have light traffic or heavy traffic, we can see. When we consider this narrowband IoT standard with 1 coverage region, what we found that, for example, when we increase the repetition factor of the preamble from 1 to 8, so the random access success probability high. It is obvious because instead of having repetition factor 1, so preamble only 1, if you have preamble repeated 8 times, so definitely it will succeed within one of these 8 intervals. So if you have 32, still random access success probability high, whether it is light traffic scenario or heavy traffic scenario. What we found that if the repetition factor of the preamble is 64, if we have 64, the random access success probability is 99%. So that means one particular device will succeed to establish the connection with 99% probability within 10 attempts if we have the repetition 64. But we cannot have the repetition factor of 64 statically, because if we fixed the repetition factor 64, we are going to waste the resources, because now maybe active devices may be 10,000. Next second, it will be 5,000. Following second, it will be 1,000. So we don't need 64 all the time. So that means during every few hundred milliseconds, this repetition factor should change. So therefore, it cannot be static. So therefore, here, if you take narrowband IoT, we have 9 parameters. So every few hundred milliseconds, so that means frame the transmission time interval. At the beginning, all these 9 parameters should be changed dynamically, because the traffic is time varying traffic, heterogeneous. So this is the second motivation we need. Why do we need artificial intelligence? So here, so I provided first one, under bursty traffic, it fails. Second one, when we take narrowband IoT standard special use case, so these 9 parameters cannot be static because of time varying traffic. So since the traffic is time varying, so the parameters also should be changed dynamically. Okay, now we are going to see what are the challenges. So if you take narrowband IoT, I told you 9 parameters should be changed dynamically. Number of preambles, random access opportunities, repetition value. Other than that, these 9 parameters, so to establish the connection, so there are access control schemes. Access control scheme means the base station control the devices to access. So access control scheme, there are few schemes. So when the base station control the access, so they have to broadcast the access control factor. So for example, you have 100 devices, base station will tell only these devices can transmit now, others cannot transmit. So that is access control. So for access control, so there are 3 main schemes. So when you take these 3 main schemes, there are 4 parameters. So if you take narrowband IoT, in addition to these 9 parameters, we have random access or multiple access control parameters 4. So 9 plus 4, 13 parameters should be optimized dynamically, autonomous optimization. So how we can do this? We can do only by artificial intelligence or machine learning. There's no other way to dynamically change these 13 parameters at the beginning of the transmission time interval. So for these 13 parameters, so in the base station, we are going to have 13 agents. So those agents dynamically change the parameters and they inform to the devices the resource configuration. So now, if you take the conventional optimization and dynamic learning-based dynamic optimization, if you take conventional optimization, so they consider it is simple, implementation friendly. So, but if you take the deep reinforcement learning approach, it is complex. This is theoretical, this is computational approach. So this one conventional is unadaptable, this one is adaptable. So conventional independent optimization, here we are going to have cooperative optimization. So that means these 13 agents, they cooperate each other such that they can improve the long-term key performance index. So that means all these 13 agents cooperatively achieve the objective. So they share the information and they achieve the reward. We are going to see what are the objectives that we are going to achieve. So this is going to be a multi-objective optimization problem, time varying traffic, heterogeneous environment. So therefore, so we cannot use the conventional approach to change this parameter. So the only option is we are going to have machine learning. So there are numerous machine learning algorithms available. So here we consider reinforcement learning. So here, if you take this problem, it's a partially observed Markov decision problem. So environment. So we are going to observe. So that means the base station, so the agent is going to observe the environment. So that means during this particular time frame, so it is going to observe, so how many preambles collided earlier, how many preambles succeeded, how many preambles idle, how many devices even after random access success were able to transfer the data, how many devices even after the success failed to transfer the data. All these are going to be, the base station is going to receive the feedback after each frame. So base station has the knowledge observation in the past. So based on these observation, in the base station, the agent are going to take the action. Action means change these 13 parameters in the case of narrowband IoT, such that to maximize the reward. So here it is partially observed. Why partially observed? So we don't know the environment completely. Say we don't know the collision process. How many devices selected one preamble and collided? So 2 devices or 3 devices. We don't know how the traffic is generated. So this second or next second, how the traffic is, we don't know. So therefore, environment is not fully observed. So it is partially observed environment. So here now, before the random access parameter, now 4 parameters. So we are going to see just 9 parameters of narrowband IoT. So if you take 9 parameters, as I mentioned earlier, for each coverage extension group, we are going to have 3 parameters. So observation here, up to t-1 interval, observations are going to be U1, U2, up to t-1 observations. Actions A1, A2. So that means actions mean what are the parameters, these 9 parameters selected in the first time interval, second time interval. All these are going to be the observation. Based on the observation, these 9 agents cooperatively, they make the decision to maximize the reward. So the action at the time interval t. So that means the action means the 9 parameters during the time interval t are going to be based on the previous observations to make the reward, to achieve the objective. Say here, just take one objective. So we are going to serve more devices successfully for long term. That is one objective. There are 2 other objectives. So we have to minimize the energy consumption. We have to minimize the delay. So there are other objectives. So we just take only one objective, that is to serve more IoT devices for long term. So if you take that, so here, so if you take the, I am not going to the one reinforcement learning algorithm, Q learning, so it calculates the Q value. So here, during that previous interval, it is going to observe these 5 values. So during the previous intervals, how many preambles collided, how many succeeded, how many idle, so how many devices successfully served, how many waiting for the next interval. After observing this, so next interval, so the agent is going to take the action. So that means the agent, 9 agents are going to select the parameters. Okay, next transmission time interval. So the 9 parameters are going to be this. Following frame different, So the 9 agents dynamically at the beginning of every frame, they inform to the devices, broadcast these parameters for every region. These are the 3 parameters you have to use the next transmission time interval. So by that way, we can improve the reward. So here, so the reward function, so we take one objective. So we'll see the other 2 objectives later. Now we want to maximize the number of devices successfully served. So when we do this, so here, so we cannot keep all the previous observation, all the previous action, we cannot keep it because of memory constraint. So what the agents could do, these 9 agents, they can store up to certain past observations and certain past actions. For example, previous 50 transmission time interval, or previous 50 or 100 observations. Observation means these 5 observations. Then the action means the 9 parameters, action 1. So during the past 50 or 100 interval. So they are going to optimize the all agents receive the same reward. So they cooperatively increase the objective using Q learning. So here, so the decision or action based on the Q value, which 9 parameters give the high Q value, that is exploitation. But we can have exploration also. So that is here we can use the exploration means we can take random action. So not the best Q value action, we can take random. By that way, we can explore the other opportunities. So when we do this, so here, whether we will be able to solve the problem using this dynamic learning based on deep reinforcement learning. So what we did, okay, we take one base station. So we consider the area of 12-kilometer radius. So we use 9 agents. Every agent, they use the deep Q-learning network. So in every Q-learning network, we have 3 hidden layers. So in every hidden layers, we have 128 neurons. So that is rectifier linear units. So we did the episode 4000 training. What we found is we can solve the problem of bursty traffic. So that means when we have these 9 agents at the base station, so we can solve the problem. So now if you see the load estimation based static one, so certain time interval is static, so it failed under bursty traffic. So load estimation based uplink resource configuration with the repetition factor 1, 4, 8, 2, 8, 16. So here blue and green failed. But these 9 agents dynamically change the parameters every 640 milliseconds. They change the parameters. They are able to serve as many devices possible, and they are able to solve this bursty traffic problem. So here we can see, so during the bursty traffic scenario, how they dynamically change the repetition factor, how they dynamically change the number of preambles for each region, how many random access opportunity randomly changes. So all these shows that so dynamic optimization solved the problem in narrowband IoT. Now we will come to the access control, that other 4 parameters. So now I just considered 3 regions, every region 3 parameters, 9 parameters. Access control means base station is control the devices. Okay, you can transmit, you cannot transmit. So therefore you have 4 devices, base station control, device 1 and 2 you can transmit, now 3 and 4 you cannot. So how this access control is done? So this is conventional. If you take cellular network or if you take a Wi-Fi or whatever it is. So here we have the access control scheme. 3 so popular schemes are there. So first access control is base station is going to send the ACB, access class barring factor, ACB factor. Every device is going to generate a random number between 0 to 1. So this device, say for example, you have 4 devices. So this one generate a random number of 0.3, 0.4, this one 0.8, this one 0.7. So ACB factor, if it is 0.5, only these first 2 devices, their random number is below the ACB broadcasting factor. So they are allowed to transmit. So now the question is, similarly backup scheme, if it fails, so the base station broadcast, okay, this device, you wait next 10 slots. So therefore backup factor, ACB factor. So in the scheme, distributed queuing scheme. So in this distributed queuing scheme, to control the access, there are 2 parameters. One is the depth of the tree and the degree of the tree. So if you use the depth of the tree and degree of the tree, 2 parameters we can change. Say for example, here we have the degree. So here we group the preambles into 3 groups, 1, 2, 3. So the device is going to select the preambles from group 1, 2, 3. Say the first time slot is going to select the preamble in the group 3. So it failed. It will have to wait till the 4th slot. In the 4th slot is going to take the preamble in group 1. Failed. It will have to wait till 11th slot. The 11th slot it will have to take not from 3 and 1. It will have to take from the pool of 2. So here we have 2 parameters. So now the question is, So base station is going to inform to the devices. So if you want to use ACB, so it has to broadcast ACB factor. So those who are below this number, you can transmit, others cannot. So similarly, back-off scheme, back-off factor. So here, two parameters. So these four parameters cannot be static. So if it is static, so all devices, say if you fix the ACB factor now, so ACB factor you fix 0.5, so these 50% of devices will not be able to transmit. So ACB factor is say 0.8, so many devices can transmit. So because traffic is time varying, so ACB factor should change dynamically according to the traffic. So these four parameters should be changed dynamically. So therefore, if you take narrowband IoT standard, in addition to these 9 agents, so we can have these 4 agents for access control. So total 13 agents. Now, if you take the thing, the problem is these parameters, access control parameters, ACB factor, back-off factor, or distributed queuing, there are degree and depth, 2 factors, all depends on the load. So that means backlog. So now the time interval now. Next time interval, we don't know the load, what is going to be the load. So if you use the conventional maximum likelihood estimation method of moment, so we can estimate the load during the current interval. And we can assume that the load in this interval is going to be the same as next interval. That is totally wrong, because now the load may be during this interval, number of active devices may be 500. We cannot say next interval also 500 is going to be there. Now 500, next interval may be 100 or maybe 1000, we don't know. So therefore, we have to predict the load, not estimate the load. If you predict the load accurately only, these 4 parameters can be changed dynamically. So how can we predict? So say if you take a estimation algorithms, the method of moment or maximum likelihood, any estimation algorithm, you can estimate in the current interval based on the observation. You cannot predict, but we need prediction, not estimation. So therefore, how can we? So here we predict motivated by this so the Google, if you take the Google translation, so LSTM recurrent neural is used in the Google translation. Using LSTM architecture in the recurrent, so it can predict this. So therefore, this LSTM is powerful time series prediction. So therefore, we can use the recurrent neural network, LSTM architecture based recurrent network to predict the load. So if you take the time slot -1, t minus 2, t minus t, next time slot t plus 1. So based on the observation, so we have to predict what is going on in t plus 1, not estimate. So estimation is during this interval, use that load is going to be the next, cannot say. So therefore, if you take the normal schemes, what they do, they observe during the interval t, and they estimate the load in t, and they in the time interval t and t plus 1 same, but that is practically not possible, because time varying 100, next interval may be 1000 or 10, we don't know. By Google Translator LSTM based recurrent neural network, we can predict the load. So if you take the architecture based recurrent neural network, so based on the previous observation 1 to up to t, so we are going to calculate the probability in the next interval. So here we are going to have an upper limit. So which value of n gives the maximum probability? So we are going to select it. So here observations are going to be of preamble idle, number of preambles fail. Those are the observations. Based on those observations, so LSTM is recurrent neural network is going to predict the load in the next interval. So now, so here if you take the recurrent neural network, we have to train the parameter theta. So to train the parameter, so we can use the cross entropy loss function. So I'm not going to provide more details. So I can provide the suitable reference if you are interested to learn. So when we use this LSTM based recurrent neural network, so here it predicts the load accurately. So what is going to be the load next interval? So here LSTM based offline and online. So offline means, so we trained using say 10 to the power 5 or certain number of episodes. We trained the recurrent neural networks because the initial value of the weight is very important. So after training, if it is online, so immediately they make the decision. So what is going to be the load in next interval? We can see. So online LSTM architecture based recurrent neural network perfectly predict the load. So the load prediction is essential. If the load prediction is accurately, if the load is accurately predicted only, the access control can be done perfectly. Otherwise, if we cannot control the access, so whether ACB vector or Backhoe scheme or distributed queuing, the 4 factors we cannot calculate accurately in the base station. So therefore, load prediction is essential. So once we predict this load, so using this predicted load, time is running out. Okay. Based on this predicted load, so here we are going to see the factors to control the random access. So here, if you predict the load NT plus 1, so the say for example, the ACB factor. If you have more devices in the load, so we are going to reduce the ACB factor. So ACB factor is going to be 1 over predicted load. So if you predict the load accurately, only ACB factor can be calculated accurately. So therefore, we can use the prediction first. So once we predict accurately, we can use that value with the random access control. Okay, so now if you don't predict, what will happen? Okay, we are not, so we have to predict. If you don't predict the load, just without predict the load, so we have only 4 agents. So for ACB factor, 1 agent. So Backhoe scheme, Backhoe factor, 1 agent, it will decide. Distributed queuing, 2 agents, they decide. So when we learn the deep reinforcement learning, there are numerous deep reinforcement learning algorithms available. So actor critic, so policy gradient, deep deterministic policy gradient, so deep queue network. But so for ACB, from the experimental results, we found that for ACB, deep deterministic policy gradient reinforcement learning gives better performance. So now we don't predict the load. So what we do is observe the environment. Observe the environment means up to previous time interval. So the observation is going to be 3 observations. How many collided, how many failed, how many idle. Based on this observation, this deep reinforcement learning algorithm select 4 parameters. So it works well. But say here, compared to the static value, based on the observation, deep reinforcement learning algorithm works well, because here you see, if you don't change dynamically, the system fails. So it's fine. But the problem is, it is going to be the convergence problem. So that means if you don't predict the load accurately without prediction, just use the machine learning to change these access control parameters, what we are going to have we are going to have the problem of conversion. It won't converge. The machine learning will not converge. So the system will not be stable. So we are going to be unstable. So therefore, what we have to do, we have to decouple the problem. That is, we have to estimate the, we have to predict the load accurately. Then only these access control parameters can be estimated accurately such that the system will be more stable and converge quickly. So because of that, what we have to do to implement, we have to decouple the problem. So that means traffic prediction based on LSTM based recurrent neural network. Then these parameters optimization for access control parameters 4, narrowband IoT parameters 9. So here to have this 4 plus 9, so that is separate deep reinforcement learning. So the prediction is based on LSTM structure based recurrent neural network. If you don't decouple this, so we will have the problem of slow conversion. So it's instability we are going to have. So when we use this decoupling, so that is the load prediction and access control. So we are going to have predicted one LSTM. Then based on the observation, so we can use the estimation. So we predicted one, but we get the results. So now, say for example, now the time interval slot is 10. So in this 10, LSTM recurrent network predict the load for the 11th interval. It predict the load is going to be 550. So in the 11th interval, from the observation, using conventional approach, we can calculate. So estimate. So now the predicted one and estimated one will not match, but we can minimize the loss. So that means in the predicted, the recurrent neural network parameters, we can adaptively change. So by that way, so over a period of time, it will converge and the recurrent LSTM based network will predict the load accurately. So the system will be stable, more stable and converge quickly. Now, so now the earlier when we take narrowband IoT, we formulated the problem, only one reward. One reward is optimize the, if the system is able to serve more devices successfully, that is enough. But in addition, we have two more objectives. So the problem now is going to be hybrid optimization problem. So that is, we have three objectives. First, we have to serve more devices successfully. That is one objective, fine. Next objective, we have to minimize the energy consumption because lifetime of the battery 10 years. We have to minimize the delay. So therefore, since we have three objectives, so here we are going to have weighted hybrid optimization problem. So here, if you take the reward, we have three sub rewards. So that means if the average access success is going to be directly proportional to the reward. If the energy consumption is more, less reward. If the average access delay is high, less reward. So that means the agents, they are going to change the parameters such that minimize the energy consumption, minimize the delay, at the same time to serve more devices. So this is going to be a hybrid optimization problem. So then, so as I mentioned earlier, we decouple the problem. So then we found that access control, we haven't considered the narrowband IoT. We just consider the access control. So three scheme, ACB scheme 1 parameter, backhouse scheme 1 parameter, distributed keying 2 parameters. We can have hybrid scheme also. Hybrid means one device first try ACB scheme to establish a connection, failed. So what it is going to do? Okay, it will try another scheme, distributed queuing scheme. It failed. It is going to try backhoe scheme. So that is hybrid. Instead of using one access control scheme, we can have hybrid scheme also. So when we see the energy consumption, so we can see when we have hybrid, less energy consumption, because the device, say if you use one scheme alone, say ACB only alone, failed again, failed again, failed again. So then it will consume more energy. But when we use the hybrid scheme, we can reduce the energy consumption. So now, as I mentioned earlier, when we decouple the problem, so here, if you don't decouple, say the different episode, so over the period, so we are going to change the training, we are going to train the deep reinforcement learning in green and blue without decoupling. If you don't decouple, so you can see when we decouple, we are going to have the black and red 10 times faster convergence. So it is essential to decouple the load prediction with the access control. So now, if you see we considered the case of narrowband IoT. When we take the narrowband IoT, we have 9 parameters, access control 4 parameters. So we can have 13 agents in the base station. The 13 agents inform the resource configuration to the devices. So now you see under bursty traffic scenario, if you have static, the narrowband IoT will not work under bursty traffic. So now we can have the hybrid. So that means 4 parameters, 4 access control parameters dynamic, 9 narrowband IoT parameters static, or other way around, 9 static and 4 dynamic. Again failed, the blue and green. When we have all 13 parameters changes, so it's better. But when we decouple, we can improve further the stability and convergence. The performance wise, when we have total 13 agents, decouple or not decouple, performance wise is okay, but it will take long time to converge. So therefore, the best way is to use in narrowband IoT 13 agents in the base stations. So these agents, 13 agents, dynamically change these 13 parameters at the beginning of the transmission time interval. But for access control, the 4 parameters to predict accurately, the estimate accurately and inform, load should be predicted accurately. Load cannot be estimated, should be predicted. So therefore, LSTM based, so motivated by Google Translator, LSTM based predictor predict the load that helps to solve the random access success, multiple access control problem. So here I haven't put any mathematical derivations or anything. If you are interested in mathematical derivation or anything, you can refer the last paper. So this year, 2021 March, the last paper provide all the mathematical derivations, all the details, all the parameters, everything, how we solve the problem under bursty traffic scenario. So that is the end of my presentation. Now, if you have questions, is Himal here?
Yes, Professor Nalanathan.
Yeah, you are here. Okay.
So thank you very much for your very interesting talk, Professor Nalanathan.
Yeah.
It was a great pleasure to listen to it.
Yeah.
The topic that you delivered is extremely timely, and I'm sure that the participant learned many interesting technical details. So with that, I would like to ask our audience to ask questions from our presenter, Professor Nalanathan. So let me open from my side. I have a question, actually two questions to Professor Nalanathan.
Yeah.
So my first question to you is,
Yeah.
what are the most important issues of massive IoT access that you envisage to be studied using artificial intelligence techniques in the coming years?
In the coming years, so you mean how these machine learning algorithms are going to be incorporated?
Yes, especially into the framework of massive IoT access.
Say if you take the 3GPP standard, so still they haven't considered the dynamic optimization in the standard of a narrowband IoT or EMTC. But as the artificial intelligence and machine learning is essential to solve the problem, I am sure that in the future versions of 3GPP reports, there is a high chance and possibility to include in the future release. But I'm not involved in this standardization committee meeting or anything, so that's what I am not able to tell in which version or which release there's a high possibility to include. But the only way to solve the massive access problem is to dynamically change the parameters. I am sure in the future release there is a high hope that they will incorporate.
Thank you very much, Professor Nalanathan. And my second question is, the success of AI techniques, as you know, highly depend on the amount of data available for training as well.
That is the main thing, because so here we use the thousands of episodes for training, mostly based on the data set we generated by simulation. But very recently we got one industrial project, so the industrial partner gave us the confidential real data. So now we are in the process of using the real data to train the network.
Yes.
Up to now, we use the simulated data set, but to be successful, we need the real data set from the operator. So now we in one of our recent industrial project, the operator gave the real data. So now we are using that real data to train under different scenarios.
Yes, Professor Nalanathan. And also, as you know, it depends on the computational power available at different, let's say, central nodes. So my question is, in that, in the case of IoT, what solutions could be deployed so that these AI techniques would become very effective? Say for, let's say, for the training amount of training data problem, as well as for scarce computational power available at different nodes.
Okay, so the computational power, say in this type of massive IoT application, the latency is not an issue. So that's what the at the base station, if we have high computational power, that is enough. But if you take the low latency, ultra level low latency applications, so we need edge intelligence. So in that case, so the federated learning is highly suitable for the low latency application. But here the latency is not an issue. So that's what, if we have high computing facilities in the base station, that would be implemented.
Thank you very much, Professor Nalanathan. So from the audience also, if you have any questions, please direct them to Professor Nalanathan so they can, he can answer these questions. There are two methods. One is you can directly ask him. The other method is if you type these questions in the chat box, I can read them for him.
Professor Nalanathan, I'm Vindhya here. I have a small question. There are several students here. They might be willing, or they might want to get more information about your research aspects, and they might want to collaborate. Is there any opportunities that the students in Sri Lanka can collaborate with you, with your research center? So it might be very useful for them.
It's fine. So we can remotely collaborate. So in terms of funding for scholarship, that is very highly competitive. But in terms of remote collaboration, it is fine. So any students interested, they can send email to me. So I can introduce my group members. They can collaborate and they can work, because due to this pandemic, so remote collaborations. So in many places, the remote collaboration become a venue. So I am happy to collaborate remotely with any students. They work in similar problems. So if they come across any problem, so I can introduce my PhD students as well as postdoctoral fellows and other group members.
Thank you very much, Professor Nalanathan. Our students might be interested on getting to know your work and collaborate with you. Thank you very much.
So as I mentioned, like from the audience, if you have questions, you can directly ask Professor Nalanathan, or you can type them in the chat box, and I will read them for him.
So can you explain the prediction through estimation? That means we estimate base moment using moment and likelihood techniques. Then we got that results to predict our you mentioned neural network. So can I know about what's the little bit about the prediction through estimation? It's a hybrid method or something?
Yeah. So here, okay, I can share one thing. Okay. I can share. Okay, 1 second. Okay, I can share the screen. One second. See here. So here if you take the moment of matching based estimator, so here we can have the expected number of ideal value. Say if you have F number of preambles, so using the general probability, we can calculate what is going to be the expected number of ideal, expected number of success, expected number of collider. So once we get this expected value, these three values, so we can calculate, so what is going to be the mean value of absolute error. So that is, say here, this one is from the observation, this is from the expected value. So we take the absolute. So then what we are going to do, so we are going to, so here we have an upper bound here. So lower bound is 0, upper bound is n max. So we put these values in this absolute error. So which one gives minimum absolute error, we select that value of n as the method of moment estimator, and we use for the next time slot. But if you take the same thing for the maximum likelihood estimator, so here we have the likelihood function or we have the probability computation for every possible values of n. So which probability is going to be maximum, we select that value. So that is the maximum likelihood estimator. If you take the recurrent neural network, so here we have observation for certain previous time interval. So here it is going to calculate the n+1, say the probability values they are going to calculate, which probability gives maximum. So here I haven't put more detail around the LSTM network. So if you have this reference, can find, I can show you this one. Show you this one. Okay. Show the screen. So this one. So if you take this 1997 paper, so you can get more details about LSTM architecture. So how the values of this soft max output, say here, using that paper you can find this one. You can, so using that paper you can find how these probabilities are calculated. So here the recurrent network we have the weight theta parameter. So how we adjust the minimize the loss function using the say here in this slide I put it here. So we use the Poisson entropy loss. So then we using the back propagation algorithm. So we move towards the negative gradient of the cross entropy loss. So by that way, we change the parameter theta here in this probability calculations. So if you contact me by email, I can send you the two relevant references, so you can get all the full details there. I haven't included in here.
Okay, sir. Thank you, sir.
So thank you very much, Professor Nalanathan. So
Yeah.
audience, from the audience, if you have, I think we have just enough time for one more question.
Yeah.
So if you have any question, please ask Professor Nalanathan. So in that case, I will hand over the proceedings to Dr. Vindya back again.
Thank you very much, Dr. Himal. Thank you for supporting us with the Q&A session. And so we have come to the end of today's session. To thank our distinguished lecturer, Professor Nalanathan, I would like to invite Secretary of IEEE Sri Lanka section, Dr. Subodha Charles. Over to you, Subodha.
Thank you, Dr. Vindya. I hope I'm clearly audible. Don't want to take too much time because I don't want to be the person standing between you and your dinner. So first of all, Professor Nalanathan, thank you very much for joining us. I missed the first part of the presentation. I'm sorry about that. Had another meeting that I could not avoid, but I'll definitely listen to the recording and get up to speed. It was definitely insightful. I listened to most of it. So thank you very much for allocating time and being with us today with the IEEE Sri Lanka section members. It's good for the students. I mean, they understand what is ongoing in the industry and in the academic world. So they'll definitely value your inputs. It will give some guidance for them to work within the universities and also to understand what sort of technologies that they should focus on if they're interested in this particular domain. So thank you very much for opening our and also the eyes of the other IEEE members who have joined this session today. Then Dr. Himal Suravira, thank you for moderating the session, coordinating with the participants and also directing questions towards Professor Nalanathan, and definitely for making it exciting, for maintaining a healthy discussion. Then also for the IEEE members who joined the session today, I'm sure you got something valuable. We would like to encourage you to stay connected with us. We'll have these kind of distinguished lectures in the future as well. So hope you got something out. We look forward to having you for the future sessions as well. So in addition to the IEEE members, we got some other participants as well attending the session. So thank you all for joining today on a Thursday evening. So with that, I think we can wrap up the session. Again, thank you very much for our speaker, Professor Nalanathan. It was great having you, sir. Over to you, back to you, Dr. Vindya.
Thank you very much, Dr. Subodha, for the thanking note. And once again, thank you very much, Professor Nalanathan, for joining with us today. And we are looking forward to collaborate with you in the future too. So thank you everyone for joining with us. Have a good night and stay safe.